Hi everyone, I'm Dilpreet Kaur, and this summer I've been working with my mentor Satapa Gura on engineering nanoparticle shape to deliver to 3D children. So, breast cancer affects 1 in 8 women in the United States alone. Doctors often turn to chemotherapy and radiation therapy to help treat their patients. Now the problem with these therapies is that it kills both healthy cells and cancer cells, causing a lot of side effects such as fatigue, nausea, and hair loss. Now, doctors are moving towards using targeted therapy to help treat their patients. Now, what targeted therapy does is uses these antibodies to help hit receptors on cells. Now, in our lab, we use nanoparticles to help deliver these antibodies to the cell. Nanoparticles are 1/100,000th the width of your hair, so they're very, very small. Now, a healthy cell has very few receptors of the ones that we're targeting, and a cancer cell has way more receptors. So when this antibody goes into our body, it hits the cancer cell way more than it hits the healthy cells, causing very minimal side effects. And what these antibodies do is they generally cause the cell to go through cell death or apoptosis. So in our lab, we've noticed in the past that nanorods behave differently than nanospheres. So here's a picture of 200 nanometer nanospheres and 350 by 100 nanometer nanorods. Now in this next image, I'm going to show you a 2D cell culture. Now in these cell cultures, notice that the blue is the nuclei of the cells and the green is the fluorescence caused by the nanoparticles. Now once we coat these nanoparticles with Herceptin, which is the antibody that we're using for breast cancer, you notice that there's a lot more green on the image on the bottom here than on the image on the top, which means that the breast cancers are uptaking nanorods more than nanospheres. And we predict this is because of the difference in surface area of the two shapes. So here you can see that there's a lot more interaction between the nanorods and the receptors than there are the nanospheres and the receptors. So leading with this idea, we continued our experiments to see how nanoparticle shape affects different things about breast cancer uptake. So my goals this summer were to create these nanorods, then coat both nanospheres and nanorods with Herceptin, which is the antibody we're using, and then use these nanoparticles in 3D breast cancer cells to analyze how differently the two particles penetrate deep into the breast cancer cells. And the difference between a 3D breast cancer cell and a 2D breast cancer cell is we're adding the element of volume that the cells would have in a real human body. So our prediction is that the nanorods will penetrate deeper into these cells than the nanospheres, for a simple reason that they are uptaken more by breast cancer cells. So the first part of my project was to take that nanospheres that are delivered to our lab and turn them into nanorods. And the way we do this is that we first coat the nanospheres in a polyvinyl alcohol film, and we let the film dry overnight. So once we have this very thin film, we place it in a metal stretcher, as you see here, and then we heat the entire device in oil. So after we pull it out of oil, or as we're putting it in oil, we stretch the nanoparticle film, and then as we stretch the film, we're turning these spheres into rods. And then we recover both sets of particles. And then the last step is to take these nanoparticles and coat them with Herceptin, which is the antibody we're working with. So here you can see the nanospheres and the nanorods that I've made this summer. And the nanorods are 300 nanometers by 100 nanometers, which is quite different from the 200 nanometer spheres we started with. Now, the really interesting thing about the nanorods that I created is that the results are very reproducible and replicable. So every single time I make a new batch of nanorods to the same ratio, they're coming up with the same shape, which means it's a very reliable method. And the last step is to coat these nanoparticles with Herceptin. So here, once we have the nanoparticles coated with Herceptin, we put it on top of our 3D breast cancer cells, allow them to incubate for a day, and then the next day we see, using confocal microscopy, how far these nanoparticles have penetrated into the 3D breast cancer cells. Now, here is an image of a cluster of 3D breast cancer cells. And here's the image of the nanoparticles that are inside this cluster. Now the red represents the nanospheres and the green represents the nanorods. And here you don't get a real good view of what actually happens. But here you can see the penetration difference of these nanoparticles. So at the bottom of this right here, you can see that there's a lot more green than there is red, which means that the nanorods have penetrated deeper into the cells than the nanospheres. Now this, just to give you an image, is how big a breast cancer cell is approximately. So there's a cluster of breast cancer cells in this image that you're seeing. Moving on, this is just a graph of the same image that I just showed you. And what I want you to notice is that 35 micrometers away from the cell membrane, there's still a peak here from the nanorods, but no large peak from the nanospheres, which just means that what you're seeing is true and that the nanorods have penetrated deeper into the 3D breast cancer cells than the nanospheres. In summary, this summer I've created nanorods and nanospheres. We've noticed that the nanorods penetrate deeper into the cells than the nanospheres. And what's interesting about this, this therapy that we're working with is that you can coat these nanoparticles with different antibodies so they can target different diseases in the cell besides breast cancer. So it's a very good platform technology. Now, for my future work, we'll be repeating what we've already been doing to further quantify our results, and then moving on to a 3D tumor cell instead of just 3D breast cancer cells, and then for further work in vivo. And I'd like to thank my mentors, Utapra Barua, Samir Mitragotri, and a grad student who worked with me this summer, Martin Baker, and EUREKA, Odie, Kevin, and Maria for always being supportive the entire year, and everyone else in the lab and the audience for listening. Thank you.